Okay, let's go ahead and get started. So today what I would like to do is complete our discussion of quantum statistical mechanics before moving on to the next topic in this course, which will occupy us for at least the next 2 or 3 weeks, and that is the subject of symmetries in quantum mechanics. But first, let me complete our discussion of quantum statistical mechanics. So last time, we started working through the example of non-interacting free particles. In quantum statistical mechanics. So, just to remind you, we imagined that we had a system where particles were allowed to live in some set of states, which were labeled by an index nu, and the total energy of the system is the sum over all possible states that the particles could be in, times the number of particles in that state, times the energy of one of those particles in that state. Okay. And this allowed us to easily compute the partition function of the theory, which is the sum over all allowed configurations of the system of e to the minus beta e plus beta mu n, where n is the total number of particles, the sum over nu and nu, beta is the inverse temperature, and mu is the chemical potential. And last time we considered the case where the particles were fermions, so that the particles obeyed the Pauli exclusion principle, so that these integers and nu had to be either 0 or 1. And this led to the Fermi-Dirac distribution. And today I would like to complete our discussion of this example by considering bosons, where nu could take any allowed value, 0 up to infinity, which leads to what is known as the Bose-Einstein distribution. So in this case, the partition function, just rewriting that formula above, we can use the fact that the exponential of a sum is the product of the exponentials to write this as a product over all allowed states nu times the sum of nu going from 0 up to infinity of e to the minus beta epsilon nu plus beta mu all to the n nu power. And this is a geometric series that can be summed, giving us what is known as the partition function of the Bose-Einstein distribution. So the sum of x to the n as n goes from 0 to infinity is 1 over 1 minus x. So this is 1 minus e to the minus beta epsilon nu plus beta mu to the minus 1 power. And this is the Bose-Einstein distribution. In order to investigate the physics of the Bose-Einstein distribution in a little more detail, let's begin calculating some of the observable quantities from this partition function. So, for example, the total number of states, the expectation value, say, of the operator n, which counts the number of particles. So of course, just staring at our formula for the partition function up here, you can see that in order to compute the expectation value of the number operator, we just need to take z inverse mu inverse times beta inverse, z inverse beta inverse times d by d mu of this partition function. Okay. Why does that work? Well, the expectation value of num of n is the trace of n times rho, so that's 1 over z times the trace of n times e to the minus beta h plus beta mu n. And if you take d by d mu, that brings down a factor of beta n, hence the factor of beta inverse in this expression for the expectation value of n. Okay, so it's then straightforward to go ahead and compute this mu derivative. So when you compute this mu derivative, you have to take the mu derivative of each one of the terms in the product over that index mu that appears here. So for all of the terms that don't get hit by the derivative, all of the factors here in the derivative of z will cancel the factors in the z inverse. So you're left with just a sum over nu of the derivative of the derivative of this. I don't know what the product analog of the word summand is. We'll call it the product and appearing in this infinite product. And so what do we get? What's that? The factor. That's an excellent vocabulary word. I haven't had enough coffee today. So what do we get? We get the sum over nu of e to the beta mu minus beta epsilon nu divided by 1 minus e to the beta mu minus beta epsilon nu, or the sum over nu of 1 divided by e to the minus beta mu plus beta epsilon nu minus 1. So in order to understand this a little bit more explicitly, so unlike the case of the Fermi-Dirac distribution, where we had a very easy way of understanding this in terms of Fermi surfaces, let me consider a particular example here, and unfortunately we'll have to do a little bit of a calculation in order to understand the physics of this expression, at least for some simple systems. So let's consider the following example. So let's consider a particle in 3 dimensions. And let's take some 3-dimensional box. Okay. So that the energy will be 1 over 2m times the momentum squared of the particle. And the momentum is going to be quantized. So if the box is a square box or a cubic box whose sides are of length L, then the momentum will be quantized. It'll just be a bunch of integers times some factor of 1 over L. Well, that has to be there by dimensional analysis. But you already know, presumably, that if you have particles in a periodic box, then the momenta are quantized in units of 1 over L, where these q's here are some vector q1, q2, q3 of integers. And then the allowed particle states, nu, are given by triplets of 3 integers q1, q2, and q3. So the expectation value of n will be the sum over the allowed values of qi, where I runs from 1 up to 3. So the sum over allowed values of q1, q2, and q3 of this quantity e to the minus beta mu plus beta epsilon nu. And what is beta epsilon nu? Well, that's beta. Here, let me write this a little more explicitly. Let's write this as the exponential of minus beta mu plus beta times the energy, so that's beta over 2m times 2 pi h bar over L squared times the length of that vector of integers q squared. And all that minus 1. Okay. Any questions on this so far? Have you guys seen Bose-Einstein condensation before? All of you? Okay. Well, you're going to see it again now. Have you seen this calculation before? No? Yes? More or less? How have you seen Bose-Einstein condensation if you haven't seen this calculation before? That's what I'm sort of curious about. Well, you're going to see this calculation. Okay. So what we reduce this now to is a very complicated sum, which is actually rather difficult to do explicitly. So let's consider, however, the following simplifying case where we take the size of the box to infinity. So the box has some linear size L, and let's take L to infinity. And in the limit where L goes to infinity, intuitively you expect that the quantization of P will become more and more fine-grained, and so that we can approximate this summation by an integral d3q. Okay. And so then, once you have it as an integral, well, you just perform the integral. Obviously, one way to do that would be to go to radial coordinates in the three-dimensional Q space, because the integrand only depends on the length of the vector Q. And then you're left with some complicated version of some sort of one-dimensional integral over the radius Q. And I'm just going to tell you what the answer to that integral is. Okay. So as L goes to infinity, this can be approximated as the sum of two terms. So first of all, there's the term that comes when all of the integers qi are equal to 0. So what is that? That's 1 over e to the minus beta mu minus 1, coming from the case where all of the integers are equal to 0, plus a term that comes when we perform that integral that I described, d3q. So rather than just telling you what the answer is, let's first notice that in front of the q vector here, we have a particular combination of dimensionful quantities. So when you have a d3q, you know that has some particular dimensionful scaling with q. So you know that there's going to be a particular combination of those parameters, beta, m, h bar, and L, that is going to appear out front. And so you can see here that q squared scales like the inverse of beta h bar squared over m L squared. So an integral d3q will involve that quantity to the 3/2 power, so that you know what you'll get out front is L cubed, otherwise known as the volume of the box, divided by something that I'll call lambda cubed, where lambda is just dimensionfully something that goes like the square root of h bar squared beta over m. And then you have some complicated integral, which will depend, among other things, on beta mu, which is a parameter that I'll call z. Well, I won't even bother calling it z. And I'll just call that integral g. So it involves e to the minus beta mu because of this e to the minus beta mu here. And, in fact, if I just choose to put a factor of 2 pi there, then g is a rather famous function. Not a famous function, but only a rather famous function, known as the polygamma. Okay. So this is the usual strategy in mathematics. If you come up with an integral or a differential equation that you don't know how to do, you give it a name and you declare that it's another special function. And so this is the special function defined by the integral that I don't know how to do that appeared in this formula for the expectation value of n. Okay. And The important observation that I would like to make, which is independent really of any of the detailed forms of this polygamma function, is that depending on the value of n over v, that is to say, on the density of particles per unit volume, which is usually denoted little n, it's possible for a finite fraction of the particles to be in their ground state. And a situation where you have a quantum system at finite temperature, for example, where nevertheless a finite fraction of the particles are in the absolute ground state of the system, is known as a Bose-Einstein condensate. It appears in nature, for example, in many different circumstances. So, for example, in superfluid liquid helium, the dynamics of that fluid at low temperature is described by a Bose-Einstein condensate. And indeed, given the expression that I've written down above, you can actually figure out, at least in some approximations, exactly at which temperature a Bose-Einstein condensate will occur. So, in order to understand that, note that that a finite fraction of particles must live in the ground state if n over v is greater than g of e to the minus beta mu over lambda cubed, or at very high temperature, where beta is going to 0, g of 1 over lambda cubed, which, using our expression for lambda, is, what is that? That's h bar squared, beta over m to the minus 3/2 power times some numerical constant, which is the value of the polygamma integral at 1 times divided by 2 pi to the 3/2 power. So that for materials where this Bose-Einstein condensate transition happens at high temperature compared to the other scales in the system, the Bose-Einstein condensation happens at a critical temperature, which is determined just by solving for this equation for the temperature. So what is that? Just staring at this equation, that is h bar squared divided by m times the density, little n, to the 2/3 power, times some numerical constant, which you find by doing that integral in Mathematica, which is 3.31. Okay. So using this simple model of a gas of non-interacting bosons, you see that we have a prediction that as you lower the temperature of this gas of free bosons, suddenly you'll have some sort of phase transition where a finite number of particles will live in the ground state rather than in the excited states. And it will happen at some particular temperature. And more important, really, than that numerical factor 3.31, which we derived, which is really a consequence of our decision to make these particles non-interacting, is the scaling of this critical temperature with all the various parameters of the system, such as the density at this critical temperature, n, h bar squared, and the mass of the excitations. Okay. So indeed, this is actually a really pretty good model for the formation of a Bose-Einstein condensate in all sorts of interesting physical systems. So that was just wrapping up an example that we began to work through at the end of last class. Before we conclude our discussion of quantum statistical mechanics, I wanted to end with at least a brief discussion of one formal and rather remarkable relationship between the theory of finite temperature systems and the path integral formulation of quantum mechanics that we have developed earlier in this class. But before I do so, let me pause and see if there are any questions. Yes?
Sorry, how did you get your expression for TC?
I just solved... so I know that there's a Bose-Einstein condensate when n over v, which is little n, is greater than this thing. So a Bose-Einstein state is going to appear precisely when that inequality is saturated. And then I solved for beta, i.e. T, at precisely the point where that inequality is saturated. Good question, yeah. Other questions? Have you guys seen that calculation before? Okay. It's worth seeing. I mean, you guys are adults now, and you can you have the power to understand phase transitions and when and why they occur. And this is one of the most important topics in physics. And actually, it's one that we're going to return to again, at least a couple more times in this class. Yeah. I should mention, by the way, that this is what is referred to as a first-order phase transition. And what is the order of a phase transition? Well, it's the order of discontinuity of the free energy as you move across this critical temperature. Meaning it tells us whether the free energy, a 0th order phase transition is one where the free energy itself is discontinuous as you cross the critical temperature. First order phase transition is one where the derivative of the free energy is discontinuous, and so on and so forth. And in the theory of, in the theory of phase transitions, the order of the phase transition is usually the most important piece of information that you need to determine before coming up with a detailed model of that phase transition. Yes?
So if temperature has to be less than some critical temperature, why do we take beta versus 2?
Good. Okay. I mean, I made a slightly slick argument here where I said, first let's take beta to be the temperature to be large compared to the other scales of the system. And then let's ask at what, just because I didn't want to have to worry about fixing beta mu. Okay, otherwise I could have fixed beta mu. So implicitly I'm assuming here that this value of T critical is large in some sense that I don't want to make precise. What is the sense? It's the sense in which it's large compared to all other scales in the system. At which our approximation might break down. Okay. Good question, though. So certainly we don't expect this to be a universal result, because in addition to assuming that we had non-interacting bosons, of course, which is just some artificial model, I also assumed that the temperature was large. This critical temperature is large compared to other scales in the system. Yeah, good question. This is often the way that life works in condensed matter physics. One can develop a model, but this model may or may not have anything to do with the reality of a given system that we're interested in studying. Because very often, the models that we can construct, as we have learned, all of physics is the description. What is the quote? Physics is that subset of human experience that can be described by coupled harmonic oscillators. Okay. Solvable models in condensed matter physics are, roughly speaking, those which can be described as coupled harmonic oscillators. Indeed, all I did is a fancy version of a Gaussian integral here. Okay. So the models that one can solve are not necessarily accurate approximations to some strongly interacting matter that might describe the condensed matter system of interest. Okay. When we discuss, starting this class actually, and later, symmetry principles in physics, we'll come up with other sorts of approximation schemes that would be useful for understanding things like strongly interacting systems. Good. Other questions? Okay. So now I want to move quite a distance from the nitty-gritty description of specific condensed matter systems to the statement that the finite temperature ensemble, namely the Boltzmann or canonical ensemble, where the density operator is the 1 over the partition function times e to the minus beta h, has an elegant and actually rather surprising and, at first sight, mysterious path integral interpretation. And indeed, the observations that I'm going to make over the next 20 minutes actually form the basis for much of the formal structure of finite temperature physics, both in particle physics and in condensed matter physics. So the basic observation is that if we want to describe the time evolution of some quantum mechanical system, then, among other things, one of the objects of interest that we need to compute is this time evolution operator, which, for a Hamiltonian that is independent of time, is e to the I t times the Hamiltonian divided by h bar. Okay. So that expression looks awfully goddamn similar to our expression for the density operator of a canonical ensemble finite temperature system, with the exception of that pesky factor of I. So in particular, we see that rho is a unitary time evolution operator if we evolve from time t equals 0 to some imaginary time equal to I beta times h bar. The density operator is the time evolution operator in imaginary time. We encountered imaginary time when we talked about tunneling amplitudes and the WKB approximation, and I promised you that we would return to it, and I always keep my promises. So, how can we make this useful? How could we turn this into a useful tool for calculating finite temperature quantities? Well, remember that matrix elements of U are computed by doing a path integral. Of course, there are many other ways of computing them, but one of them is by using a path integral. So that if, for example, you're working in position space and you wish to calculate the amplitude for a particle to move from an initial position at time t equals to 0 to a final position at time t, then you perform an integral over all possible paths that begin and end at the desired endpoints. So, since rho is equal to U, the time evolution operator evaluated at some imaginary time up to some normalization, which we'll return to in a minute, that means that one way of calculating the matrix elements of the density operator is to imagine all possible paths that our particle could take, say, if we're considering an object moving in one dimension, which begin at time t equals 0 at x initial, and at some imaginary value of the time, which is equal to I beta h bar, x final, weighted again by this phase e to the is over h bar. And what I would like to do now is remind you, or rather, I suppose tell you, because this isn't exactly what I said earlier, that there is a nice way of thinking about this phase e to the is over h bar. If we simply remember that e to the is over h bar, well, what is this? This is I over h bar times the integral dt of some Lagrangian x and x dot, which is a function of x and x dot. And this time is integrated now from here, 0 up to a time I beta h. So now we're viewing time as a complex coordinate, and this is a contour integral in the complex time plane, and it's an integral along the imaginary time axis. And if we simply make the change of variables, where t is equal to it Euclidean, so t is purely imaginary, and t Euclidean is real, so then dt is I times dt Euclidean. So then this exponential e to the is over h bar is the exponential of minus 1 over h bar times the integral dt Euclidean, where t Euclidean is now real. It goes from 0 up to beta h bar times the Lagrangian. And because the Lagrangian is a function of x dot is dx by dt, when I rewrite that in terms of t Euclidean, I guess I should write that as I times, I guess it's really minus I times dx over dt Euclidean. And so we typically give a name to this quantity. We call it L Euclidean. And we give a name to that integral. We call it the Euclidean action. And this expression for the matrix elements of the density operator then says that they are the matrix elements of this density operator, where you sum over paths of your particle going through a Euclidean, going in a Euclidean time direction, an imaginary time direction, where x at t equals 0 is xi, and x at t Euclidean equals to beta h bar is equal to x final. And the important thing to note is that t Euclidean is a real variable, and that L Euclidean is a real function of x and x dot, provided that L is quadratic in x dot. If L is quadratic in x dot, so for example, if we're describing a particle with a kinetic term 1/2 mv squared, then when you take t to it, that v squared just picks up a minus sign. So the overall signs in the action might have changed, but the action is still real. The Euclidean time coordinate is real. And so the way that we would approximate, for example, this density matrix in the Euclidean time formalism is exactly how we would approximate the time evolution operator U in the Lorentzian time formulation. Namely, you would look for solutions of the Euler-Lagrange equations that come from varying the Euclidean action with respect to the path, and the leading contribution would come from the saddle point approximation, it would be the exponential of the Euclidean action evaluated on that path. So all of the same techniques that we have used to study time evolution operators in Lorentzian signature can be used to study the calculation of density operators simply by making this complex change of coordinates where t is replaced by it Euclidean. Any questions so far? I'm going to take this a bit further and tell you some things that are even more remarkable. Yes?
Can you just remind us of the interpretation of that matrix element for xi equals xi?
Well, rho is an operator. So, if you're taking the matrix element of a unitary time evolution operator, then that has a natural physical interpretation. It's the amplitude for a particle to move from one place at one time to another place at another time. Now, rho is something a bit more formal. It's something that I defined to you as the operator associated with our ignorance about the exact quantum state of the system. And for that reason, I don't have a direct physical interpretation for its matrix element. All I can tell you is that the matrix elements of an operator determine the operator and vice versa. So this is the representation of the operator in the position space basis. Okay. If you think of rho as a matrix, then in the position space basis, it's an infinite by infinite matrix, and these are its matrix elements. In a sense now, what I'm doing is I am teaching you exactly what the physical interpretation of those matrix elements are. They are the matrix elements of the operator that generates time evolution in an imaginary time by an amount beta h bar. Okay. Now, of course, the time evolution operator in real time is unitary, but once you take t equals to I beta h bar, this is no longer a unitary operator. Instead, it's a Hermitian operator. Questions? Okay. So, as we have learned, one of the most important quantities that one needs to calculate in thermodynamics is the partition function. And the partition function is the trace of the quantity that I described above. So z of beta is the trace of e to the minus beta h, or the integral dx of the matrix elements of the density operator along the diagonal. So what is that? That's the integral dx of the integral over all possible paths that start at Euclidean time equals to 0 equals to x, and end at Euclidean time equals to beta h bar, also equal to x, because x initial now is equal to x final, weighted by e to the minus Euclidean action over h bar. So it's the integral dx, where x is just a number, times the sum over all paths through Euclidean time that start and end at the same point, which I could write a little more succinctly as the integral over all paths which are periodic in Euclidean time. So the partition function is the sum over all paths that are periodic in Euclidean time. And this actually gives an extremely useful approximation scheme. So remember that z of beta for a standard quantum mechanical system is the trace of e to the minus beta h. So otherwise known as the sum over all of the energy eigenstates, En, e to the minus beta En. So if we know z of beta, we know the energy eigenstates. More specifically, we know the energy eigenvalues and their degeneracies. So, for example, this tells us that we now have a dictionary which lets us determine the complete spectrum of the Hamiltonian simply by doing a Euclidean path integral. If you can perform the Euclidean path integral in Euclidean time and view that as a function of the periodicity in Euclidean time and compute that function of beta, then you should be able to read off the complete spectrum of the Hamiltonian. For example, you could look at the limit where beta is going to infinity, that is to say where t is going to 0. That's a Euclidean path integral where the periodicity in Euclidean time is very long. And the leading contribution of that should be e to the minus beta E naught, where E naught is the energy of the ground state. So for example, this tells us how to approximate the energy of the ground state in terms of a path integral in Euclidean time as beta is going to infinity. Now, we're interested in general in doing more than understanding the spectrum of energy eigenstates. Of course, in finite temperature physics, we're interested in computing expectation values. So let's consider the case where we have some observable that is a function of x. So we want to compute the expectation value of the position squared, or something like that. Then let's imagine that we want to compute its expectation value at finite temperature. What is that? Well, that's the trace of rho times A. Or if I want to expand this out in a position space basis, this is the integral dx dy of the matrix element of rho between x and y times the matrix element of A between y and x. I guess since I pulled out that factor of z, I should write that as e to the minus beta h. And A, I've decided, is a function of x, so it's diagonal in the position space basis. So I could write this as z inverse times the integral dx A of x, now just a function of x, times the expectation value of e to the minus beta h in one of these position eigenstates. And we see that this is exactly the same sort of path integral that we considered before, but now with an insertion. So that integral dx A of x times the diagonal element of the Euclidean time evolution operator, e to the minus beta h. What is that? That's an integral over all paths, which are periodic in Euclidean time, And I'll call the value at t equals 0 little x, or maybe I should call it something else. I'll call it x naught times e to the minus s over h bar with the additional insertion of a as a function of x naught. Again, divided by the partition function, which is that same path integral, but without the insertion. So we see that the way that you calculate the unitary, so we learned earlier in this course that the way that you calculate Euclidean unitary time evolution operators is by doing a path integral. And we see now that it also can compute for you the expectation value of any operator you like. The rule is that instead of taking the integral of that phase, e to the is over h bar, or in Euclidean signature, e to the minus s over h bar, you insert in the path integral the expression for the operator that you're trying to compute, regarded as a function of the configuration space variable x. And then there's this normalization factor in the denominator where you divide out by that same path integral without the insertion of the observable. And this is the expression for the expectation value of an operator in the path integral formulation at finite temperature. Okay. So thermal correlation functions, the upshot of this, are found by performing a path integral in imaginary time with a periodicity beta h bar. And it's important here to remember that this is some sort of formal trick where we view the dynamical variables in quantum mechanics as analytic functions of time. And we change the usual expression for the action in terms of the integral as a Lagrangian into an expression for a contour integral. And now it's a contour integral in the Euclidean time plane, where we integrate now over a circle. So if you want to think about it in your head, you should think about taking the complex time plane and wrapping it up into a circle, okay, or wrapping it up into a cylinder, so that Euclidean time is periodic with period beta, and Lorentzian time is the horizontal direction, which of course is infinite. Okay. And the way that you insert a density operator into your trace is you take your Hamiltonian and you integrate it along this contour. So remember, my definition of a Hilbert space is a space where I can do calculus with whatever I want. That means I can do contour integrals with whatever I want. Okay, I suppose I should say the Lagrangian. So the Euclidean action is found where I take my Lagrangian and you integrate it along this contour in the complex time plane. But we've folded up the complex time plane in order to make it periodic with period beta. Are there any questions? This might seem like a bunch of formal nonsense, but in fact, this is really the way that we, in practice, do computations for finite temperature systems. Because in practice, if you have some very complicated system, determining the Hamiltonian and exponentiating it to get e to the minus beta h is a very difficult thing to do. But what we have seen here is that we can calculate in an approximation scheme very easily by thinking about this as a Euclidean path integral. So for example, in the semi-classical limit, where we regard h bar as being small compared to all other scales in the problem, then you can calculate approximately the density matrix by finding the classical solutions of the system, but not classical solutions in the usual time, classical solutions in this funny imaginary time. So for example, if you take a system and you heat it up to finite temperature, and you want to calculate the decay rate of that system, then the way that we do it is very similar to the way that we calculate decay rates in quantum mechanics. So we saw earlier when we looked at the WKB approximation that one easy way of calculating transition amplitudes or tunneling amplitudes was by looking for the action of some Euclidean quantum mechanics system. We see here that the exact same thing works for finite temperature systems. Okay. Let me, before ending, tell you about one simple consequence of this. So let's consider the two-point function or Green's function of a system describing a particle moving in one dimension, for example. So how do I define that two-point function? Well, it's the expectation value of x at 0 times x at t. So it's the quantum, it's the expectation, it basically is computing for you the probability for a particle to move from a time position x at t equals 0 to some other position at time t. And let's compute this at some temperature beta and ask what this Euclidean time formalism tells us about this Green's function. Maybe I should restate something I said earlier. The best way of physically thinking about this Green's function, so this is a function of time, and what is this function of time telling you? It's telling you that if you perturb the system by hitting it at time t equals 0, what sort of response are you going to get at some later time t? So you imagine perturbing the system by acting with the operator x at time t equals 0, and asking what sort of response you would get at some later time t. So for example, in a system at 0 temperature, if you have the harmonic oscillator, for example, this will be a periodic function of t. Okay. There'll be some periodic function with periods set by the frequency of the harmonic oscillator. Let's now ask what we can conclude about this Green's function or two-point function more generally based on these considerations. Well, what is this? So let's write this as the trace of x of t, x of 0 times e to the minus beta h. But let's write out everything in terms of unitary time evolution operators. So what is x of t? Well, it's u dagger of t, otherwise known as u of minus t, times x of 0 times u of t times x of 0 times, here, let me rewrite this on the next line so I have a little bit more room. So this is the trace. Oh, now my pen is not going to write. Oh, there it is. What is it? It's the trace of x of t, x of 0, times e to the minus beta h, which is u of I beta h. And I can use the fact that x of t is u of minus t times x of 0 times u of t times x of 0 times u of I beta h. Now, I'm using here the Heisenberg time formalism instead of the Schrödinger formalism. Remember that as far as the computation of expectation values, the Heisenberg and Schrodinger pictures are identical. So I'm free to use whichever one is most convenient for me. Okay. So now let's use the cyclic property of the trace to move this u of I beta h over here, and use the fact that unitary time evolution operators add, u of t1 times u of t2 is u of t1 times t2. So what is that? That's u minus t plus I beta h times x of 0 times u of t. And in order to make this expression here look a little nicer, I'm going to write u of t in a funny way. I'm going to write it as u of t minus I beta h bar times u of I beta h bar. Okay, I haven't done anything there. I've just rewritten u of t times x of 0. And let's use the cyclic property of the trace again. That's the trace of x of 0 times u of minus t plus I beta h times x of 0 times u of t minus I beta h times u of I beta h. And what is u of I beta h? That's just the density operator, e to the minus beta h. So what is this? This is the expectation value of x of 0 times the expectation value at time, which is a Euclidean time, or rather a shifted time, t minus I beta h bar. So what we see is that for a finite temperature system, we have this funny relationship between the two-point function, or the correlation function, at real time and the correlation function at some complex time. In particular, regarded as a function of t, so let's call this g of t, then g of t is periodic in imaginary time. So, for example, you can see that if you shifted by 2 I beta h bar, then you would get back the original ordering where x of 0 sits on the right instead of on the left. And so you see that g of t is a periodic function in imaginary time. So this is very interesting. It means that if you're studying a finite temperature system and you want to understand the response of the system to a perturbation as a function of time, then you could view that as a function of real time if you like. But you could also view it as a function of complex time. And if you did, you would find that it's a periodic function in complex time. And so indeed, one of the things that we like to do is Fourier expand this in signs in the sign of omega t Euclidean. So we Fourier expand this in the Euclidean time direction. And we end up with some mode expansion in the Euclidean time direction in terms of some characteristic frequencies that are known as Matsubara frequencies. And this is a very interesting and useful way of understanding the behavior of correlation functions in finite temperature systems. By the way, I should say that there's a name for this relation. We usually call it a KMS relation. I unfortunately don't know who K, M, and S were. I assume K was Kubo, but I'm not sure about the others. Probably some Russians. It's usually how it works. Okay. This completes what I had planned to say about quantum statistical mechanics. Let me pause and see if there are any questions. Is this Euclidean time stuff completely, does it seem like formal nonsense to you? Or does it seem interesting? Those aren't mutually exclusive, I suppose. I mean, the reason why I introduced this is that it's something that actually, as far as practical computations go, is very, very useful, because all of the perturbation methods that we develop in physics that allow us to approximate path integrals can then be applied to systems at finite temperature. And there's a whole theory of physics the theory of quantum field theory, not just quantum field theory, but including quantum field theory, devoted to the discussion of perturbative techniques to approximate path integrals. And so very often, people on the fourth floor who study finite temperature systems spend a lot of their time applying those perturbative methods to compute things like finite temperature correlation functions. So for example, you often hear about Feynman diagrams. What are Feynman diagrams? Feynman diagrams are just a very simple diagrammatic trick that we use to keep track of perturbative corrections in the saddle point approximation in quantum mechanics. And because of this set of observations, those Feynman diagrams are equally useful if you want to try and compute any sort of finite temperature response function, such as a Green's function or a conductivity or something like that of any material at finite temperature. Okay. Questions? Okay, so we've now completed one of the most fun parts of this course, namely the part on quantum statistical mechanics. And we're moving on to another really fun part of this course. Equally fun. You couldn't possibly get me to choose between them, which is the subject of symmetries in quantum mechanics. Before diving into a detailed discussion of symmetries in quantum mechanics, I would like to spend at least one page of notes talking about symmetries in classical mechanics. So, what I would like to recall, or what I would like to remind you of, is that symmetries have profound consequences in classical physics. In particular, perhaps the deepest and most important results in classical mechanics is Noether's theorem, important enough that my daughter is named after Noether, but don't tell my wife that, which is that symmetries are in one-to-one correspondence with conserved quantities. Every time you have a symmetry, such as a translation symmetry, a rotation symmetry, a gauge symmetry, a Lorentz boost symmetry, and so forth, you have a corresponding conserved quantity, such as a linear momentum, an angular momentum, an energy, a charge, energy momentum, and so forth. And the implications in quantum mechanics are equally striking, but will require a little bit of reinterpretation. And it will require us to develop a little bit more formal language to understand the implications of symmetries in quantum mechanics. Before doing so, I would just like to remind you of how life works in classical mechanics. In classical mechanics, a symmetry is a transformation of our dynamical variable Q that we use to describe the state of a system where we change coordinates on configuration space to write things in terms of some new dynamical variable Q tilde, which leaves the action S unchanged. For example, if you have a system which is translationally invariant, then shifting X by a constant does not change the momentum, and so the Lagrangian and hence the action are unchanged. That is the description in the Lagrangian formalism. In Hamiltonian formalism, a symmetry is a canonical transformation which leaves the form of Hamilton's equations unchanged. So let me remind you exactly what that means. So recall that a canonical transformation is a change of variables in phase space. So instead of describing a system in terms of a position and canonical conjugate momentum P and Q, we will use a new position and conjugate momentum Q tilde and P tilde, which preserves the fundamental Poisson bracket so that Q tilde with P tilde, the Poisson bracket, is equal to 1. So what does that mean? So let's investigate that in a little bit more detail. So let's consider a continuous symmetry. Namely, a one-parameter family of symmetries, a one-parameter family of canonical transformations, so that we could imagine doing an infinitesimal canonical transformation, so that Q tilde will be not equal to Q, but equal to Q plus some very small bit proportional to epsilon, and likewise for P, then the statement that the Poisson bracket is preserved can be expanded order by order in powers of epsilon. So the leading term, of course, is just 1, and the term linear in epsilon will be the sum of two terms, the Poisson bracket of delta Q with P and that of Q with delta P. And if we remember that the Poisson bracket of two observables A and B is just the derivative of A with respect to Q times B with respect to P, plus the same thing with P and Q reversed, then this is 1 plus epsilon times the derivative of delta Q with respect to P, plus the derivative of delta P with respect to Q. Simply because the derivative of P with respect to Q is 0 and vice versa for Q with respect to P. So that means that changes of variables in phase space, which are, continuous changes of variables, and in particular an infinitesimal change of variables in phase space, which is a canonical transformation, has to have the property that all of the terms in this expansion in powers of epsilon have to vanish. And so that means that delta P and delta Q aren't completely independent, but that they are related in some way. So in particular, delta Q and delta P have the property that the derivative of delta Q with respect to P is equal to minus the derivative of delta P with respect to Q. What does that mean? That means that there is some function on phase space, so a function of Q and P, i.e. an observable, so let me not call it a function, let me call it an observable, such that delta Q is the derivative of G with respect to P, and delta P is minus the derivative of G with respect to Q. Sorry, I got that backwards. Then you see if you took that and you plugged it into this equation, that equation would necessarily be true by the equality of mixed partial derivatives. I'm sorry, I totally got things backwards. I've gotten my Q's and P's mixed up. You should really mind your P's and Q's. Get it? That's Q. Is that why you guys are whispering? Or no, you're whispering for completely different reasons. Okay, so delta Q is dG by dP, and delta P is dG, the derivative of G with respect to Q. Good. Or, to say this a little more succinctly, Q tilde is Q plus epsilon times delta Q, which is dG by dP, and that could be written as Q plus epsilon times the Poisson bracket of G with Q, and likewise P tilde is P plus epsilon times dG by dQ, which is P plus epsilon times the Poisson, with a minus sign, which is P plus epsilon times the Poisson bracket of G with P. Which reminds me that that's a minus sign there. Sorry about that. You guys all knew that. I assume the reason why nobody bothered to correct me is that was such an obvious mistake that you thought it completely trivial and not worth wasting our time to correct. But let me remind you that it's always worth correcting a trivial typo like that. Okay. So what does this mean? This means that canonical transformations, at least infinitesimal canonical transformations, are generated by observables via the Poisson bracket with that observable. And G here is referred to as the generator of the corresponding canonical transformation. So we've seen that Q tilde is Q plus epsilon times the Poisson bracket of Q with G. P tilde is P plus epsilon times the Poisson bracket of G with P. And so, in general, if you ask how A, some more general observable changes, under this transformation, A will go to A plus epsilon times the Poisson bracket of G with A. Why is that? Well, if you just regard A as a function of Q tilde and P tilde, well, you could expand in a power series in epsilon, that's A of Q and P plus epsilon times, I shouldn't write a curly bracket there, times the derivative of A with respect to Q, delta Q, plus the derivative of A with respect to P times delta P, Delta Q is given by dg by dp. Delta P is given by minus dg by dq. And we have there nothing more, nothing less than the expression for a Poisson bracket. Okay. The moral of the story being that a continuous family of canonical transformations, that is to say, or at the very least an infinitesimal canonical transformation, is generated by a particular observable associated with that canonical transformation. Have you guys seen this before? Have you seen it? You saw it in your classical mechanics class? Okay, good. It's worth dwelling on. It's a very important point. Okay, so that's a general word about canonical transformations. Now what about symmetries? So a symmetry is a canonical transformation which preserves the Hamiltonian form of the equations of motion. So remember that Hamilton's equations tell us that q dot is dh by dp, otherwise known as the Poisson bracket of h with q. And more generally, if you have some other observable, say q tilde, our new dynamical variable, that is going to be the Poisson bracket of h with q tilde, which, if we consider a canonical transformation that is generated by some observable g, then that is the Poisson bracket of h with q plus epsilon times the Poisson bracket of g with q plus higher order terms. So that is equal to q dot from the Poisson bracket of h with q plus epsilon times the Poisson bracket of h with the Poisson bracket of g with q. And we can now use the Jacobi identity, which is the fundamental identity obeyed by Poisson brackets, commutators, and the like, to rewrite this as epsilon times the commutator of g with the commutator of q with h plus the commutator of q with the commutator of h and g. Sorry, I should say Poisson bracket, not commutator. And what is this first term here? Remember, G is the generator of canonical transformations. So this is the variation of Q dot under the canonical transformation. So the time derivative of Q tilde dot is equal to Q dot plus the variation, epsilon times the variation of Q dot, only if the Poisson bracket between H and G is equal to 0. So the form of Hamilton's equations is preserved only if the Poisson bracket of H with G vanishes. So a symmetry in classical mechanics is a canonical transformation which is generated by an observable G whose Poisson bracket with a Hamiltonian is equal to 0. And this has two implications. The first of which is that the time derivative of G is equal to 0, because the time derivative of an observable, according to Hamilton's equation, is the Poisson bracket of G with H. And the second is that the variation of the Hamiltonian under the canonical transformation generated by this generator G is equal to 0, because that is also the Poisson bracket of G with H. Thus, we see that there is a one-to-one correspondence between conserved quantities and symmetries of the Hamiltonian. Questions? This is presumably all familiar to you. Am I correct in assuming this? Okay. Sometimes in classical mechanics courses, this is not presented in quite the same language that I'm using. I'm really emphasizing the formal language of Poisson brackets and canonical transformations because it's precisely those things that become commutators and unitary operators in quantum mechanics. So next class, we'll discuss in greater detail the theory of these symmetries in quantum mechanics. So I'll see you on Friday.